Real derivatives are telling us something about the slope of the tangent line. And that's a very geometric meaning you can attach to this derivative number. But with analytic functions, like complex derivative, what does that number tell us? It's not as easy because we can't draw like a two-dimensional graph with something very straightforward like a slope. But in this video, I'm going to give you some answer to that question. So here we go. Before we go further, I'd like to make sure we have the same terminology on things that we're going to discuss. So hopefully you've seen this in a different class as well, but let me review some terminology. So we say the function is injective, or it's an injection, also called one-to-one function, if different input implies the outputs are also different. So that's injective function. A function is surjective, or it's a surjection, sometimes also called onto, if for every y in the target or the range, there exists an input such that it hits that number. So every element in the range is hit by some input. We also say the function is a bijection, sometimes also called one-to-one correspondence, if they're both injection and surjection at the same time. Okay, so let's review these concepts applying to some complex functions that we know. So let's focus on the function z squared, but I'm going to look at a different domain and range than usual. Okay, so here I'm going to look at the domain of the real part is positive. So that's the right half of the complex plane. And if each of these numbers are squared, so remember the square doubles the angle. So the angles you can get on this the right half plane is anywhere between negative pi over 2 to positive pi over 2. If you double that when you square, you'll get. I didn't leave myself a lot of room to draw this. You'll be able to get all the angles from negative pi to positive pi. But you will exclude the negative real axis because the domain excludes the imaginary axis. So you don't quite have angle negative pi over 2 to pi over 2. And when you, so the argument is between negative pi over 2 to positive pi over 2. And making this argument doubled, it will be between negative pi and positive pi. I hope that makes sense. So if we start from the right half plane and map to all the complex number except for the negative real axis, this is a bijection. Because every point in the range is hit by some number. So you could just take this angle, divide it by 2 and get the right argument. And the modulus is going to be the square root of that modulus. And no other numbers when squared is hits the same function. So it's injective as well. Okay. If you view the function z squared, in the whole complex plane, then it's not injective because two different numbers could have the same square. For example, -1 and +1. If you square it, you get 1. It doesn't happen in the previous picture because only one of them is in the domain that we're looking at. Okay, so if the domain is the whole complex plane, it's not injective, but it is still surjective. Every point in the complex plane has actually two different square roots that map to it. If you're looking at the square root function, that goes from the complex plane minus the negative real axis, then it's injective, but it's not surjective because, for example, it misses 0, right? Since 0 is excluded from the input, you cannot hit 0 in the output. The only thing whose square root is equal to 0 is 0. So, okay. I hope that made sense. So we're going to use those terminology. I'm going to introduce this concept of conformal mapping. So I'm going to talk about intuition first because the actual definition takes a little bit of work. And so intuitively, conformal mapping is a mapping that preserves angle between curves. So let's say we have some domain and we have some curves, like smooth curves living in that domain. And if you apply the map F, that will distort the picture in some way. And it might change the shape overall, but the angle at which these curves intersect does not change. Okay, so that's a special type of mapping. It doesn't change the angle there. Okay, so to make that idea more precise, we need some definitions. So let's say a path in a complex plane from A to B is a continuous function, let's say on an interval, on a real interval from A to B, such that the starting point is A and the ending point is B. So you can kind of imagine it starts at the complex number A, and as the variable changes, get closer to B, it'll continuously move to the point B. Okay, a couple example of path. So if you look at the path e to the it from t between 0 and 2 pi, so this is a familiar path to us. So it starts at 1 because e to the 0 is 1. And as t increases from 0 to 2 pi, it will trace the unit circle in a counterclockwise direction. So this is a path from 1 to 1. So it starts and ends at the same location. Okay, here's another path. It's a multi-part function, and it starts at 0, and as t changes from 0 to 1, it goes from 0 times 1 plus I, which is 0, and it goes up to 1 times 1 plus I, which is 1 plus I here, and it does so in a linear way, from going from 0 to 1. When t is equal to 1, and as it increases past it, it switches the formula to t plus I. So when t is exactly equal to 1, it's still at 1 plus I. So if you plug in 1 here, we're going to get 1 plus I. But as t increases towards 2, the imaginary part is fixed at I, and the t increases up to 2. Okay, so now it gets to 2 plus I when t is equal to 2. And when t is equal to 2 in the third formula, it still starts at 2 plus I, but as t increases, the imaginary part decreases until it hits 0 when t is equal to 3. So this is a path that starts from 0 and it ends at 2. And he makes 3 line segments. That kind of looks like that. Okay, so we could have smooth curves like this, and you have kind of jaggedy curves like this, but they both kind of traces some kind of path in a continuous way. Okay, I wanna say that the path is smooth if you look at this function. So let's say x of t and y of t is the real and imaginary part of this path. You could take derivative of both of those, x and y. So the first path satisfies the smoothness condition all the way through because it traces a circle that's a differentiable thing. In fact, it's cosine and sine function, so we know what the derivative is exactly. This function right here is not differentiable when the formula switches over when t is equal to 1 and 2. But it is still differentiable anywhere else, right? So when you have a situation like that, we'll say it's piecewise smooth. We have maybe finitely many points where it's not differentiable, but everywhere else in between, the derivative exists. So we call that piecewise smooth. Okay. And when the derivative exists, we call that the derivative the tangent vector of the path gamma at z naught, if it's at that location. Okay. All right. Now we're ready to formalize what it means to have angle of intersection of curves. Okay, so let's say you have 2 smooth curves, gamma 1 and gamma 2, intersecting at some point z naught. We say the angle of intersection between the curves at z naught is the angle between the 2 tangent vectors. So here, this is the tangent vector for the first curve, gamma 1. That's the tangent vector for the gamma 2. And you find the angle between those 2 vectors. I say vectors, but these could be interpreted as a complex number as well, right? Where the real part is the first component and the imaginary part is the second component. Okay, so let's do an example. Okay, so let's say we have these 2 curves. Let's draw them. Okay, so gamma 2 is the unit circle starting from 1 going counterclockwise. So this thing we know how to graph. Gamma 1 is it's t times 1 plus I. Okay, so when t is equal to 0, it's at the origin. And when t is equal to 1, it hits 1 plus I. It's linearly moving from 0 to 1 plus I, and I guess, and further if t is larger than that. Okay, so they clearly intersect on the unit circle when that line hits that circle. We know that that point, which will happen at 45 degrees, or I guess pi over 4 radians from the origin. Okay, so that location is 1 over root 2, or cosine of pi over 4, which is 1 over root 2 plus I over root 2, which is the sine of the pi over 4. Okay. Note that these two curves do intersect, but it intersects at different t's, right? So t is equal to 1 over root 2 for the first curve, and t is equal to pi over 4 for the second curve. So the t's do not have to match, but at those two t values, these curves are sitting at the same location at this point. So this is our z naught. Okay, so let's see the angle of intersection here. We can take the derivative. So the derivative of t plus it is going to be 1 plus I. And derivative of e to the it, we could just use a chain rule. E to the it times the derivative of it, which is just I. Okay. And we should plug in the actual t value to get the tangent vector at that point. So gamma 1 evaluated at 1 over root 2. Well, that's still 1 plus I, because the derivative is the constant 1 plus I. Okay. Gamma 2 prime evaluated at pi over 4 is going to be I times 1 over root 2 plus I over root 2. So that will be negative 1 over root 2 plus I over root 2. Okay. So that curve looks like this. So that tangent vector looks like this, and the tangent vector for the first curve looks like that. Okay, so maybe from geometry, maybe you already know that that has to be at 90 degrees, because it's a line through the center. It's going to be perpendicular to the tangent line to the circle. But let's just do this computation. So there's a couple different ways to compute this. You could use the angle of between vectors formula from calculus 3. If you remember that, it's this guy. So we could use this. So arc cosine of the first vector, 1 plus I, and we could, in the vector notation in Calc 3 class, that's what that looks like. And the vector for the second curve is negative 1 over root 2, comma, positive 1 over root 2, divided by the magnitude of each vector. So the magnitude of 1 vector is root 2. And magnitude of the second vector is equal to 1. Okay. Well, the computation is actually not that bad, because when you do the dot product in the numerator, we'll just get 0. And arc cosine of 0 is pi over 2 radians. Okay. So that's one way to compute it. Another way to compute it is looking at the difference of the argument of the two complex numbers. So the angle for the first tangent vector is 45 degrees. So this is a tangent vector that points 1 plus I, so 1 unit to the right and 1 unit upward. This is pi over 4 minus the angle for the second tangent vector, So that's a vector that goes negative 1 over root 2 to the left and positive 1 over root 2 upward. This is going to be the angle of 3 pi over 4. Okay. So the difference of the angles is going to be negative pi over 2. Okay, so it makes a 90-degree angle. So there's a couple different ways to compute it. I prefer you use this method. Use the argument function and look at the angle of each tangent vector and then look at the difference between them. The reason being, in this setting, the positive or negative angle matters. So the orientation of the angle, is the angle to the clockwise direction or counterclockwise direction makes a difference. Okay, so um, uh, I, I prefer you compute it this way, but as long as you're paying attention to which curve is where, you could still use Calc 3 method as well. Okay, so the definition, a function is conformal at z naught if it preserves the angle between the curves at z naught. So before and after the function, you still have the same angle. And conformal mapping between two domains u and v is continuously differentiable mapping at each point of view that is bijection. Okay, so this definition might be slightly surprising because we just defined what it means to be conformal at a point, and the definition of conformal mapping doesn't talk about the preserving angle, right? It's just asking you to be bijection and continuously differentiable. So it's complex analytic, and it has to be a bijection at the same time. So this definition might be slightly mysterious, but it's actually not mysterious if we keep in mind of this theorem. So it turns out that if you have an analytic function such that the derivative is not equal to 0, then f is conformal at z naught. Okay, so as long as the derivative is not 0, it's conformal. That's a big statement, right? I mean, it seems very complex to keep a function so that the angle doesn't mess up at every point. But actually, it's almost automatic if the derivative is not equal to 0. Well, let's see the reason. Actually, the reason is dead simple. So let's say you have a curve, and the curve passes through some point z naught. Let's say when the input is t naught, in somewhere between a and b. So let's see how the angle changes with this map. Okay. So we're looking at the image, so f of gamma of t, or f of gamma, and we take the derivative so look at the tangent line at the image. To take the derivative, we just use the chain rule. So f prime of z naught times gamma prime of t naught. Notice how this is the tangent vector before the map, and the tangent vector after the map is just multiplying by the derivative at z naught. So it actually doesn't matter which way the curve is coming in at z naught or which way it's leaving. The only thing that the map does, only thing that analytic function does to the curve is that it just multiplies by the derivative. And what does that do to the picture? Well, basically you're multiplying by a complex number. And remember, the complex number multiplication is a combination of the stretch factor with the magnitude and also the rotation factor with the argument. Um, and that's all it's doing. It's a stretch and a rotation. It doesn't change the angle because it's stretching in the same way to all directions. I hope that makes sense. And if you have two curves, right? So we have f of gamma 2, take the derivative. Okay. The second curve is going to be stretched and rotated by the same factor. So if you have two vectors and you stretch everything by 2, the angle doesn't change. It's the same angle that's being stretched. And obviously the rotating the angle doesn't change anything because both angles, both tangent vectors are being rotated by the same amount. So if you look at a curve and apply analytic function to it, as long as the derivative is non-zero, the angles do not change. So let's think about this. We have the function z squared. And let's say it's, we know it's a bijection between the right half plane and the, I guess the slit complex plane. We just discussed that earlier. If you have any curves, okay, they're going to be stretched and deformed, but the angle at that point does not change before and after. Okay, which I think is amazing. Well, actually, we have to look at the derivative. So the derivative of z squared is 2z. The only way this could be 0 is if we're looking at the origin. And origin is not part of the domain, so it's conformal everywhere else. Okay, so this transformation doesn't change angles of any smooth curves. So maybe I could draw a more interesting picture. So let's say I write high on the right half plane, just kind of tilt your head 90 degrees. And if I square it, it'll look something like this. It'll be distorted. High will be, this is supposed to be the H. And this is supposed to be the I. I don't know if you can see this. The I got stretched this way, and the H got stretched heavily that way. Okay, so it's a distorted high in the output. These straight curves have turned to curvy curves. It's no longer straight, but all the 90-degree angles that were there before the map is preserved. So all these angles will still appear as angles of 90 degrees, all of them, which I think is really cool. Okay. Um, but for the z squared to be conformal, we must stay away from 0. Okay. Okay, so a couple more comments, right? So the function e to the z is conformal at each point in the complex plane. The derivative is never equal to 0, so you don't have to worry about that part. But it's not one-to-one, because remember, it's 2 pi I periodic, right? So if the imaginary value goes up by 2 pi, we get the exact same value again. So if you kind of restrict yourself to maybe a domain, it's like a horizontal strip where this height of this strip is 2 pi, then this complex exponential function does not repeat itself. So if you're working in this domain, then it's one-to-one. So now it's a conformal map. So this conformal map will take this horizontal strip with 2 pi, and then it will, let's see, what would that do? So it would map to everything except for the positive real axis. So it will get all the argument between 0 and 2 pi. Okay. One last comment, which I kind of already mentioned earlier, is that the orientation does matter. So the complex conjugate function z bar, it is one-to-one, and it is onto from C to C. Basically, what it does is it'll take everything above the real axis and flip it to below the real axis and vice versa. If you have two curves there, you'll just get a vertical reflection of those curves in the image. But the angle changes in a sense that the orientation changes, right? In this picture, gamma 1 is sitting in counterclockwise direction from gamma 2. In the reflection, it's the opposite. It's going in the clockwise direction. So we won't count that as conformal. So z bar is not a conformal map. Okay, so hopefully this gives you more insight into what complex different derivative is, right? So the derivative will locally, overall, there could be distortion, but if you look near that point, the only thing that function is doing to the curve is that it's stretching by some factor and possibly with some rotation. That's the only thing it's doing. Okay,